Hello and welcome back to Calculus 1 section 5.3 on fundamental theorem of calculus. Well, let's see what's so fundamental about it. It has two parts. Part 1, you already know. It's the way to compute definite integral, and if everything is above x-axis, it will give you the exact area. So a equals integral a to b of f of x dx is equal to the any antiderivative f of x computed from a to b, which is calculated as f of b minus f of a. So that is the fundamental theorem of calculus part 1. It's a definite integral and it computes area under the curve as long as everything is positive. If the area dips below x-axis, as we discussed in a previous section, you will have to chop off that piece, put the absolute value on it to bring it up, and then add all of the areas to have a total area of what it needs to be. So that's that part. Important sentence that we need to write here is that value of the definite integral is not always the same as the area under the curve. And I can just draw two graphs and everything will be clear because we already discussed all of these problems. You know what you're supposed to do to fix this. So that's part 1. What we are focusing on, we know all about it, so we're just gonna focus on part 2 of the fundamental theorem of calculus. So here goes part 2, fundamental theorem of calculus. So fundamental theorem of calculus will have one formula. So if f of x is continuous on closed interval a and b, you need to close the interval because a and b are the endpoints of integration, so you must have them. Then, and now we have the derivative of the integral from a to x of f of t dt is equal to f of x. Huh? What?
Why wouldn't the integral be a to b?
It's a to x. We will see why.
And why? Alright.
We'll see why, but please tell me what, the hell, is going on over there. What is this equation trying to say? Something obviously fundamental, but what is the fundamental idea? We already mentioned that idea, but now you have the formula for it. What does that say? That line.
That's sort of like linear division.
No. Do you have anything that is the same on left and right? Okay.
It's like the derivative of the function according to t in respect to x is equal to function x.
You are getting closer, actually. You missed one word which made what you said, unfortunately, untrue, but you are getting so close. You needed one more word in that soup of words you used. I just need someone to translate this mathematical equation into the common language, because let's say you tattoo this across your back, right? The entire back. And then someone at the beach says, "What's that?" Now you know they're not good with math because they're missing at least half of their teeth, all right? So now, how would you explain in one word, one sentence, what this is?
Integration is the opposite.
Thank you. Done deal.
Even Google it.
Integration and differentiation are opposites. We already talked about that. That's 4.9, antiderivative. Guys, the derivative of the integral, they cancel each other out. Like a square root and a square. Like ln and e. Except those are function inverses. These are operators. So, you know opposite operations. Addition and subtraction are opposite operations, right? Square root and square, opposite operations. Well, for these guys, which are operators, the opposite operators from each other are derivative and integral. So now, we would like to see why and how. The first order of business here is to just run this calculation, which will answer your mysterious x question. I have to do the proof. Oh, by the way, this is a theoretical section. We actually don't have problems that we compute here. There is a proof for this, and then the two concepts, the part 1 and part 2. So let's do this calculation. I have the derivative of the integral of f of t dt, so t is the main variable, and the limits are a to x. So I copy the derivative, and the integral of function f is the antiderivative capital F, which is computed from a to x. Are we all good with this? We know from part 1, we know that the integral of lowercase f is the uppercase f, and we use uppercase f to denote antiderivative. So, if I find the antiderivative for lowercase f, that antiderivative of lowercase f is going to be capital F. So now, we use the part 1 to compute, and this is where you get f of x minus f of a. We're good there, right? So now, do we all agree that x is a variable, a is a constant? Do we all agree also that f of a, the whole thing, is a constant then? Right? If, let's say, f of x is equal to x squared, what is f of 2? It's going to be 2 squared, which is 4. So f of a is a constant. What is the derivative of the constant? 0. So the derivative of antiderivative is the original function plus 0, and there's your f of x. If the integral of f is capital F, the derivative of f is lowercase f, right? Did we say that you can check your integration if you take the derivative and you get this, you got it? So there it is. Derivative of that into that.
So everything in black is just
The proof
larger
of
explanation, or the proof of
the proof of red, yes. Everything in black is the proof of red. Now, it's just calculation for it. Now, guys, do we all agree that if I write f of t is t squared, f of x is x squared, is the same thing? Right? Same thing, just different letter. We call that dummy variable, substitution. That's what the t is up there. Because we have to save x to have the answer in terms of x. So that's cool. Now, that formula technically says that whatever function of t you plug in here, let's say t squared, you are going to get the same thing on the output, because these two essentially cancel each other out. So it just swaps the variable, but you get the same function out. So what does the fundamental theorem of calculus say? Part 1 tells you the story of definite integral, calculating definite integral, and the meaning with the area under the curve. And the part 2 tells you, or the fundamental theorem tells you, that derivatives and integrals cancel each other out in the same function. Now, my question to you is, why are derivatives and integrals opposites?
wasn't integral was the inverse, like what you're undoing the derivative. You're giving
What you said is 100% correct. I just want to know why. I have so many whys at this point. Why are they opposite? Is there something that could help us if we write down that we could possibly look at and then maybe make a case why they're opposite? Like, what would I even write? I'm asking, why are derivatives and integrals opposite of each other? Why do they undo each other?
Would it be like the same reason why trig functions and inverse trig functions cancel out, or not really?
Not really, because trig functions are functions. Integrals and derivatives are not functions, they're operators. So you have the world of numbers, world of variables, world of operations, world of functions, world of operators, and they all have their own realms of things. Yes? The derivative will give us the slope of the tangent line, which measures the change. Integrals measure the accumulation. But those two concepts are not necessarily opposite of each other when you apply them. That's just application. I'm asking what types of, if we can write something down to see why are integrals and derivatives opposites of each other. What is the only thing that you can actually write? If you want to research, learn about something, what would you write? Not the function. These are operators. You would write the definition of them. What's the definition for the derivative? Definition, the limit definition. You had it on your exam too, and both of you did it right.
It's f of x plus h.
Yes, but before that is
The limit.
the limit h goes to 0. Okay.
X plus
x plus h.
minus f of x divided by h.
Great. Perfect. Now, how about the integral? How about the integral? What do I write? All you need to do is to flip page or 2 pages ago.
Isn't the limit as
N approaches infinity.
it's
Summation.
As
I goes from 1 to N. Uh-huh.
delta x.
Nice. Okay, cool. We mastered to write these two. Now we're staring at these two definitions. Definition for the definite integral, definition for the limit. Both are limit for derivative. Both are limit definitions. Why are these two opposites of each other? Why is derivative opposite of integral? Why is integral opposite of the derivative? Can you look at the definitions and tell me? Now, it's too obvious, so it is very hard to see it. What happened? How do you see continuity?
One limit's approaching 0.
Okay, I'll take the limits approaching 0 and the other one's approaching infinity. There's something way more fundamental, well, two things way more fundamental than that, but at least I'm happy that you are looking at the 0 infinity.
You have a positive fxi and a negative fx.
You are getting very close. I never actually heard anyone say that particular thing, but you are getting very close. What is... Yes?
Wait, one is like the limit as the difference is approaching 0, and
We already
did.
hopped off of the limit train, so
Sorry,
let's
oops,
not mention
sorry.
limit anymore. What is different in these formulas?
Oh, multiplication and division.
Thank you! Derivative has a big fat division in the middle, and integral has times delta x, has multiplication, right? Perfect. What else? I want one more just like that.
In the integral, we're taking the sum of everything, and on the top, we're taking the subtraction.
There we go. Do you see that these two formulas are completely opposite of each other? You are subtracting, you're adding, you're dividing, you're multiplying. Right? They're completely opposite of each other. Of course they're going to undo each other, right? And if you go and say, oh, but when you have this over here at the plus, yeah, I do. I also have b minus, right? A in this one, right? Do I? I do. So all of the operations within these are opposites, right? We have pairs of all operations, and then on top of that, we're going to slam that limit difference you said, right? One is going to 0, the other one is going to infinity. These are two fundamentally different concepts, as you mentioned, right? One is calculating the slope of the tangent line, which measures the change. The other one is calculating accumulation, which is area under the curve. So if you are to apply these concepts to a word problem, and this is what I like to discuss at the end, you can go and you can say the population in time for rabbits that started with 500 rabbits in whatever habitat, and they are multiplying at the rate e to the, let's say 3t, whatever, right? You put whatever is there. You have a model formula for a population of rabbits in this habitat. No predators, they have infinite amount of cabbage, and they can just thrive, right? Yay. Now, that positive 3 guarantees that the population of rabbits will grow. Now you're going to say, okay, how many rabbits am I going to have next year? Well, that's simply going to be P of 1, and that's going to be 500 e to the 3. You punch these numbers in a calculator. Can anyone quickly please compute 500 times e cubed? Please do not give me decimals because be nice
It's,
rabbits.
10,042.
10,042. It's a lot of rabbits. They are really busy.
Well, if you want to round up 43, but
Yeah, 43, yes. 10,043 rabbits next year. There we go, right? If I want to know the amount of rabbits in 10 years, then it's going to be 500 e to the 30. Now that's going to be a large number, right?
hold on. You want the decimal in this one or not?
No decimals. These are rabbits.
Then 5.
What is like 5.7 of a rabbit? Okay, so you have a 5.
5, 3, 4, 3, 2, 3, 7, 2, 9, 1, and then a couple of zeros. It's times 10 to the 15th, so I don't know. I didn't count that. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then add 6 zeros.
Several zeros.
Alright, add 6, 0, 1, 2, 3, 4, 5, 6. That's why they say multiply like rabbits, right? Look at that. The good thing we have a fox and a car. Huh? Oh, you never chased a rabbit with your car? Me neither. I'm just checking. I want to know who are all the people that are sitting in the. All right, this is a terrible function, but such is life. All right.
Yeah, 5.3.
All right, so now this is pre-calculus. You have the formula, you plug in the number, you get the value on the other end. That value represents the number of rabbits that you have after time passed, right? This is a terrible problem, but we got it. Now, enter calculus. Calculus can answer a lot of stuff for this, and we are going to have in Calculus 2 an entire section that deals with this. But now it's worth to mention that you can differentiate this, and you will get 1500 e to the 3t. Now this formula will tell you how many new rabbits you add in a particular year you are interested in. So now you can calculate the amount of new rabbits by computing this. So again, I'm not going into details here because you are going to have a full lecture of this in Calc 2. So amount of rabbits added in any one particular year. So you can calculate, because it calculates the change, and it can calculate the change at the point, so in 2 years, so you would have p prime of 2, and that will tell you we added this many new rabbits in that 1 year. So that's what it calculates. And then you can integrate over the range t1 to t2, which is, in this case, 500 e to the 3t dt. That will give you 500 over 3 e to the 3t computed from t1, t2. This over here will give you the total number of rabbits present in years t1 to T2. So you can say, what is the total amount of rabbits? Because remember, the number of rabbits from year to year changes, right? You have 500 rabbits to begin with, and after a year, you have 1,000 rabbits, let's say, and then the next year you have 2,000 rabbits. So what is the total amount of rabbits? Well, you added a certain amount of rabbits, right? So it calculates the amount, the accumulation of all rabbits that were there from whatever years you pick. Not just the new ones coming in, that's the derivative. This calculates the old ones and new ones, right, all together on the pile. Now, by the way, this is a terrible, terrible model. All of these rabbits are immortal. Right? All of these rabbits have no predators. All of these rabbits have infinite food. They are resilient to diseases. No one drives around them. So I never hit a rabbit in my car, all right? But I always love seeing when Easter rolls around, I love to see that picture of the rabbit and those eggs going down the highway. You've seen that, you probably. Some of you are laughing, so you know what I'm talking about. That and the kid crying next to the Santa's grave. Anyway, so these are the concepts. And finally, just because we can, you can also show that this is a terrible, terrible, terrible model by working out the limit as time goes to infinity of 500e to the 3t, and you will get that if you wait a very long time, you will have a population of infinitely many rabbits, which we know it's not possible because every habitat, including this planet, is finite. You cannot fit infinite amount of anything on the finite surface area. Like even if you think that the Earth is flat, please jump check. It will still be the finite area, right? You will just use the area of the circle. But finite areas cannot contain infinite amount of rabbits or humans or whatever. So that's what we have. Great. Yay, done. Tomorrow is Friday. All right, we'll skip tomorrow.
And Saturday and Sunday.
And Saturday and Sunday?
Yeah.
Now you're pushing it. So Monday, 5.4, it's a very short section. Bring your labs in on Monday so you can also do some work. We'll also have review. So Monday is a short lecture, maybe 30 minutes. Not that bad. We are introducing 4 formulas. And that's it. And then we'll do the labs, we'll do the review. Tuesday, first thing is the exam. And after the exam, remember the chain rule? And I said, if you don't know this, right, don't bother with the rest of the course. Well, 5-5, if you don't know this, don't bother signing up for Calc 2. Because it's going to be half of your course in that 5-5 section. So that's going to be after the exam, and then review on Wednesday, and finals on Thursday. So, bye.